Scientific method, a planned, orderly procedure applied to solving a problem to produce facts and accurate evidence to support a conclusion. So the first step is to identify the problem. And a lot of times this is something that can be detected by any of your five senses. So you would see something happen and then ask, why did this occur? Number two, gather evidence. So before I go out and start solving a problem, maybe somebody else already did this, or maybe someone else had started to do this, so I'm going to take the research that they have and work with it before I go on and pretty much start from scratch. Number three, make a hypothesis. So a hypothesis, we learned in elementary school, was an educated guess, and it's called an educated guess because you base it on facts that you know to be true. Number four, we're going to test the hypothesis. So this is actually carrying out the experiment. Then we're going to observe and record. So that means that we're going to keep accurate and up-to-date records of all observations. And if somebody was to come and repeat my experiment, they need to have identical results. So after I make conclusions, again, this has to be something that can be repeated. So now we have the difference between a theory and a law. So a theory is an explanation backed by results from repeated tests. Now theories can change over time based on new information. So before 1969, we had a theory that the Earth was 3.5 billion years old. So how did we have this theory? We had the theory because when scientists found all kinds of rocks on Earth, they saw that the rocks on Earth, the oldest rocks they found, were 3.5 billion years old. But something changed this theory. So in 1969, we went to the moon, and when we went to the moon, we brought back rocks, and the rocks on the moon were 4.6 billion years old. Actually, I think they thought the Earth was 3 billion, so because there was a difference of like 1.6 billion years, which that's huge. So what was the difference? Well, first of all, that's assuming that the Earth and the moon formed at the same time. Will we ever know if the Earth and the moon formed at the same time? No, because we can't go back in time to know for sure. So why aren't there any rocks on the Earth that are 4.6 billion years old? Well, the Earth is very dynamic. So between weathering, erosion, plate tectonics, and everything else, that's why we don't have rocks. But again, this is a theory because we don't know for sure that the Earth and the moon formed at the same time. So that's why a theory is an explanation based on facts that we know to be true. But theories change over time as we gather more information. Even you learned about the theory of plate tectonics in Pangea. We don't know that there was definitely one giant supercontinent. We have a lot of evidence. We have fossils. We have glacial erosion. We have all this other stuff that supports the theory of plate tectonics, but we don't know for sure. Where a law is a scientific rule or principle. So a law is a scientific rule of nature that describes the behavior of something in nature, but doesn't explain why it will happen in a given situation. Now, most laws, especially in physics, they're expressed in an equation. So we have Newton's 3 laws of motion, which a lot of you have already learned, the laws of thermodynamics, and things like that. So the biggest difference between a theory and a law is that a theory is much more complex and dynamic, whereas the law governs a single action. Then we're going to start to measure. Measurement is important. Man's been having to measure for years and years. So when man first started measuring, there's a lot of things that they measured. We looked at, they measured the pyramids. We see they built bridges, and obviously there were a lot of things that they had to measure. But it wasn't until in Europe where countries started trading with one another where they realized that they needed something that was standardized. Standardized means everyone is using the same thing. So that's when we say a standard, this is a fixed quantity to which all measurements are compared. So that's what it means by standardized. So people were using all types of things. In England, the king was using his foot, but there's a lot of problems, and then people were using their hands and other parts of their bodies and things like that. But there's problems with that. So in France, the international system, which we abbreviate SI for System International, this is based on the number 10, and this was easy because back in the 1700s when they were using this, a lot of people, they didn't have a higher education, so they could use their 10 fingers to count. So this was easy. So the standard unit for length is a meter. For volume, it's a liter. For mass, it's a kilogram. For temperature, it's degrees Kelvin. And for times, it's second. So a fundamental unit is one or more standard units. So just a meter, a liter, a second. A derived unit is two or more. So if I was to measure area, a meter times a meter is a meter squared. So that's a derived unit. If I was to measure volume, a meter times a meter times a meter is a meter cubed. That's a derived unit. If I was to measure density, and the equation for density is mass divided by volume, so mass in grams divided by centimeters cubed gives me gram per centimeter cubed, which is also a derived unit. Now, a meter is kind of big. And if I was to measure something really small, like we're going to do in our density lab next week, a meter is too large of a unit. So we have something called a prefix, and a prefix makes a unit larger and smaller. So the prefix always comes first and then the unit. So the example is if I have a little m and I have two of them, the first one's going to be the prefix and the second one's a unit. So this is millimeter. Now the prefixes are in your book on page 12, and I'll also give you a handout. So there's different ways that we can convert. So today we're going to do easy conversions where we're just moving the decimal point. And then tomorrow we're going to do more complicated conversions where we have things in the numerator and the denominator. But in order, dimensionally consistent means that you can't add things together unless they're the same. So I can't say a meter plus a meter per second. This measures length, this measures speed. So whenever you're looking at things, you always have to look at the units to make sure that they're correct. Now the great thing about physics is we have a foolproof way to always check our work no matter what. Because if we carry our units through and cancel them, we'll always check and make sure that we don't make an algebra mistake.